Colligative properties. Properties that depends on the number of particles dissolved in a given mass of a solvent are called colligative properties. They do not depend on the chemical nature of solute or the solvent. Colligative properties of solubility. Solubility is the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. Solution is a homogeneous mixture of two or more substances. When solute is introduced into the volume of solvent, the solvent properties will change. There are four types of colligative properties of solution. First, vapor pressure lowering. Second, boiling point elevation, freezing point depression, and osmotic pressure.
So vapor pressure lowering, it occurs with an addition of non-volatile solute to a solution in order to lower the vapor pressure of the solution. So the solute molecule will occupy some of the spaces, and this will then affect the solution and the vapor pressure due to the fewer solvent molecules that will be vaporized. So basically in this diagram, it shows that if the pure solvent, you can see that the vapor pressure is very high due to more particles that will be vaporized. But when we add a non-volatile solution, it will then lower the vapor pressure because the solvent contains solute and this will occupy the surface area. And then with fewer solvent particles at the surface, so then the particles that will vaporize will also be lower, and this will then lower the vapor pressure.
For vapor pressure lowering, it's explained by Raoult's law. Raoult's law says that the vapor pressure of a solvent is directly proportional to the mole fraction of the solvent in the solution. Basically, it means that when the vapor pressure increases, the mole fraction decreases and vice versa. So we can see the equation here, which is P1 equals to X1 multiplied with P01. P01 is the vapor pressure of the pure solution. So this is the equation. And additionally, as the solid is added, the vapor pressure drops.
Example question for vapor pressure lowering. Calculate the vapor pressure of a solution made by dissolving 218 grams of glucose given molar mass equal to 180.2 grams per mole in 460 ml of water at 30 degrees Celsius, and it is given pressure of water equal to 31.82 millimeter mercury. Assume the density of the solvent is 1.00 gram per ml. What is the vapor pressure lowering? So first, we have to calculate the number of moles of glucose and water in the solution using the formula. To find the number of mole of water is equal to 460 ml divided by 18.02 gram, and it is equal to 25.5 mole. And next, we have to find the number of mole of glucose equal to 218 gram divided by 180.2 gram, and it is equal to 1.21 mole. Next, we have to find the mole fraction of water. X1 is given by X1 equal to N1 divided by N1 plus N2 using the formula. So from the value we obtained, we have to substitute into the formula, which is 25.5 mole divided by 25.5 mole plus 1.21 mole. It is equal to 0.955. Next, we have to find the vapor pressure of the glucose using the formula pressure equal to X times pressure initial, which is 0.955 times 31.82 millimeter mercury. And finally, the vapor pressure lowering is 31.82 millimeter mercury minus 30.4 millimeter mercury, and it is equal to 1.4 millimeter mercury.
As for the boiling point elevation, one consequence of Raoult's law is that the boiling point of a solution made of a liquid solvent with a non-volatile solute is greater than boiling point of the pure solvent. The boiling point of a liquid is defined as the temperature at which the vapor pressure of the liquid equals to the atmospheric pressure. For a solution, the vapor pressure of the solvent is lower at any given temperature. Therefore, a higher temperature is required to boil the solution than the pure solvent. Any addition of non-volatile solute to a solution raises the boiling point of the solution above that of the pure solvent. When a solute is dissolved in the solvent, the boiling point of the solution is raised. According to the equations, delta T is equal to I kBm. Delta T is the change in temperature. As for the I, is the Van Loff factor, which is the number of particles into which the solute dissociates. As for the M, it is the molality, which is the moles of solute per kilogram of solvent. And for the Kb, it is the molar boiling point constant. Okay.
Question. We add 475 grams of sucrose, which is sugar, to 600 grams of water. What will be the boiling point of the resultant solution? Solution. In order to find number of mole of sucrose, we take mass of sucrose divided with molar mass of sucrose, giving us 1.388 mole of sucrose. Thus, in order to find the change in temperature, we need to find the molality. So, we take number of mole of sucrose divided with mass of water, giving us 2.313 molality. By using the formula of change in temperature, we take the constant K, which is 0.512 Celsius, times with the molality, giving us 1.18 Celsius. To find the boiling point, we need to add the external temperature and the change in temperature to find the boiling point. Thus, the boiling point is equal to 101.18 Celsius.
Next, about freezing point depression. Addition of a non-volatile solute of a solution lower the freezing point of the solution relative to the pure solvent. The equation for this freezing point depression is when the change in freezing or melting point is equal to the freezing point depression constant multiplied with the molality of the solution. The freezing point depression constant value only depends on the solvent. The molarity depends on the concentration of solute. For the diagram above shows how the substance added to the water can hinder it from freezing. For the system A, the particle in this solid can easily shift into the liquid phase at the normal freezing point temperature as shown by the arrow. For the system B, however, the particle in this solid cannot shift into the liquid phase at normal freezing point temperature because solute particles block movement from solid phase to liquid phase.
Okay, we move on to the freezing point depression example question. We add 475 grams of sucrose to 600 grams of water. What will be the freezing point of the resultant solution? So the solutions are: sucrose have the molar mass of 342.30 gram per mole. And from there, we find the mole of the sucrose by dividing 475 grams of sucrose to 342.30 gram sucrose per mole, and we get the result of 1.388 mole of sucrose. Then we find the molality of the sucrose, which is 2.313 molality, and then we use the equation that shows the change in freezing point equal to the freezing point depression constant K subscript F times with the molality of the solution. So from the information that we get, we fill in the information to find the change in the freezing point, and then we get the result of 4.30 degrees Celsius, and that's it. So we minus and we got the result is negative 4.30 degrees Celsius.
Osmotic pressure. Osmotic pressure is the passage of solvent from more solute due to concentration solution through a semi-permeable membrane. For example, is the diffusion of water through a semi-permeable membrane from a solution of a low concentration to the solution of high concentration. In osmotic pressure, the osmotic pressure is a minimum pressure which need to apply to the solution to prevent interior flow of water across the semi-permeable membrane. For example, is the pressure needed to stop the osmosis. You can see the three steps, which is the initial step, equilibrium, and the external pressure applied. In the law of the osmotic pressure, the law is the Boyce-von Hoff law, which is, you can see the formula is the pi volume equal to nRT. The pi is equal to IMRT. The Charles von Hoff law for solution is a combination of two laws. We get Van Hoff law. So you can see this is the formula.
Alright, now let's have a look at the important terms of osmosis and osmotic pressure. We have isotonic, hypertonic, and also hypotonic. Isotonic is a solution which have equal concentration of solute and also equal osmotic pressure, while hypertonic is a solution with higher concentration of solute, and lastly, hypotonic is a solution with lower concentration of solute. The application is in water desalination. A large external pressure is used to push the solvent molecule water from seawater through a membrane to producing drink water. And the exercise provided here is, we have three questions. The first one is calculate osmotic pressure for 0.1 molar Na3PO4 at 20 degrees Celsius. Since temperature is provided, molarity is provided, then we can use the formula pi is equal to mRT directly by just substituting the value inside. So we will get 9.6 atm. The second question, calculate molarity of solution in water at 300 Kelvin, which has osmotic pressure of 3 atm. Since we know that pi is equal to mRT, so we just change the formula a bit and make it to become m is equal to pi over RT. Sub the value inside and we will get 0.122 molar. The third question, hemoglobin is a large molecule that carries oxygen in human blood. So a water solution that contains 0.263 gram of hemoglobin Hb in 10 milliliter of solution has an osmotic pressure of 7.51 torr at 25 degrees Celsius. So what is the molar mass of the hemoglobin? Since if you see here, the pressure provided is in torr unit, so we gotta change it into atm. Yeah, then we just type the value inside the m is equal to pi over RT to get the molarity. Then from the molarity of 4.0389 exponent negative 3, we can find the number of mole, since we know that n is equal to mv. So we just take the molarity time with the volume provided, which is 10 exponent negative 3. We will get 0.0389 exponent negative 6 mole. And last step, we use the molar mass is equal to mass over number of mole. We sub the value, then we will get 65116.73971 gram per mole.